Good morning. This is AP Calculus BC. We're taking a look at section 10.2, the calculus of parametric equations. But first, let's look at the homework that was due today, a review of parametric equations. On number 49, there was an error on the solution sheet. I arbitrarily picked 34 as the period of the motion along this hyperbola. I decided to start at time zero here. I mean, those are the two main options for the starting points. I picked this one. Instead of going up, which would have been a positive tangent function for y as a function of t, I picked going down just to show you how much freedom you have in modeling real world situations. So if I pick 34 for the period instead of 2 pi, which is just the standard period for a secant function, then halfway through I'm at 17. Either way, the graph of x as a function of t is a secant function. By the way, whenever you have a hyperbola, the parametric equations are going to be either secant with tangent or cosecant with cotangent. When you have circular motion or elliptical motion, it's going to be sine with cosine. But the point is, because I decided to go down, that means that y as a function of t ended up being modeled by a negative tangent function. That negative sign was not on the solutions when I initially posted them. It's corrected now. Any questions on either this problem or any of the other homework questions from assignment 10.1? Edward?
How do you trace the graph of a hyperbola? Which way does it go first?
It's up to you. I mean, this is a real world situation. There's some particle, maybe it's a friend of yours at the mall who's decided to wander aimlessly through the mall in a hyperbolic path. You're just trying to create a mathematical model of that. They decided to go down. They could have started here and gone up, in which case it would have been a positive 3 tangent function.
So if you go up here, where do you go after you get to infinity?
Well, you go infinitely far that way, and then you travel infinitely far. You just, in a zero time, you travel infinite time to come up here this way. So, but this, if you were to trace it, because that's what you asked about. If you start here, starts here for the first, whatever 25% of 34 is seconds, and then the second 25% of 34 takes you here, so times 17, you're there halfway through the cycle. The third 25% of 34 takes you along that half branch, and the final 25% of the journey takes you here, so time 34, you're back where you started.
Why does it go that way? Not go like this?
Well, if you study the parametric equations of hyperbolic motion, you see that it's a secant function, and secant functions, the x-coordinate starts at 4, goes up to infinity, flips over to negative infinity, so it's all tied to the graph of the secant function that underlies the hyperbolic motion. Further questions on assignment 10.1? All right, so we're going to jump into assignment, or the lesson for 10.2. So there's a review section here. Please pull up the review, or page 1 of Calculus of Parametric Functions. Assignment 10.2 is due the Tuesday that you get back from break. I hope that you also attempt to complete the 2012 AP exam. Here we go.
Sorry,
Problem 1. Oh, yeah. Question?
On the last question.
Last one. Go ahead.
71, I just don't know how to do it.
Problem 71?
Yeah.
Okay, let's talk about problem 71 a little bit. And so projectile motion is really linear motion with gravity accounted for. So in this situation, analyzing the baseball's flight projectile motion starting at 0,3, they tell you that the horizontal component is 100 miles per hour. The horizontal speed is 100 miles per hour. That's accounted. We have to convert 100 miles per hour to feet per second. I use stoichiometry to do that to get about 146.7 repeating feet per second. If you have questions on that, see me outside of class. Now, in order to break this initial velocity vector v sub 0, into its horizontal and vertical components, I have to use sine and cosine. So here's the magnitude of the initial velocity in the x direction, and here's the magnitude of the vertical component of the initial velocity. So that's going to be crucial.
Where's the 15 degrees from?
It's given information. If you read the problem, they start out, the initial angle is 15 degrees.
Wait.
So just,
It does?
yeah, you just got to read the problem. Just gotta read the problem, they tell you 15 degrees.
No, it doesn't.
Yeah, it does, it does. Ball hit,
A.
leaves the ball at an angle theta degrees with, okay,
We're
and then
not
they tell
applying
you, use theta equals 15 degrees.
Wait,
So
where?
in general, it'd be theta, but I just skipped to part B where it said 15 degrees.
Oh, okay.
Because that's the first one that we actually use is 15 degrees. So you have to start somewhere, add something every so often. So we're adding, this is basically the speed in the x direction. Here's the speed in the y direction. And if it weren't for gravity, the ball would just take off in a line. It would go in that straight line. But because of the gravity term, which we derived earlier in the course, it's 1/2 acceleration due to gravity. Acceleration due to gravity on planet Earth is negative 32 feet per second per second. Half of that is negative 16. So those are the parametric equations. Given the goals that we have to accomplish today, if you have further questions on parametrics of projectile motion, see me outside of class, we'll do that. We're now going to shift to assignment 10.2. Any other time that we have, we'll take to look at questions. So here we go. 10.2, the review. First of all, reviewing the definite integral of e to the x squared dt. Thankfully, there's a mismatch between x and t, so you really don't have to do anything other than treat e to the x squared as a constant. When you integrate a constant, it's e to the x squared. Just think of it as 5. The antiderivative of 5 with respect to t is 5t. So this would be e to the x squared times t, evaluated from t equals 0 to t equals 3. That one is just meant to review how important it is to pay attention to the variables. Whereas if it's e to the x squared with respect to x, now we're talking a situation in which we have to do what? Who recalls how to approach the definite integral when we don't have a mismatch, but we actually have to deal with it? What's one word that comes to mind for where to go to move forward on this? How am I going to find the antiderivative of e to the x squared? A u substitution will not work. Integration by parts does not work. Liate, the shape, fails. What do? It's one word. It begins with an S.
Substitution.
No, u sub doesn't work.
S. Sleep. Don't have to do it. You don't know how to do it.
Series. The summation. Series e to the x is one of the big four. So it's a summation from n equals 0 to infinity of x to the n over n factorial where we substitute in. So there's a little bit of substitution here. X squared to the n over n factorial. That's the approach you'd have to go from there. Just trying to keep your head in the game because we're getting close to the AP test. We've got to have the whole course at the forefront of our minds. And now, baby Elia Lynn, that's my daughter. Back in the day when I first started teaching calculus, my daughter had just been born, pretty much. And so here she is. She's crawling along this line. It's a parabola whose vertex is at 4, 6. Opening down, she's traveling along that line, starting at the point 5, 5. Sure enough, the point 5, 5 is on the graph of this parabola whose vertex is at 4, 6. And the derivative of her x parametric equation with respect to time is -6. dx dt is the derivative of the x parametric equation. What this means is that, remember, for parametric equations of motions, whether it be projectile motion, it's often you start somewhere. We're starting at the point 5, 5. And in the x direction, she's moving at a speed of -6 feet per second. So that's just like on the baseball problem where they say we're moving 100 miles per hour, which is 147 or 146.7 feet per second. So she's only going -6 feet per second, so it's like -6t. It's a linear function. And you might have seen all the freedom that you have in creating parametric equations. Oftentimes, you can make up whatever you want for the x parametric equation as long as it's a function of t, and then just plug it into the y equals menu or into the y equals equation to get the y parametric equation. Now here we don't have freedom to make up whatever function of t that we want for x of t, but so because we actually conform to the givens. But now to get the y parametric equation, it's just I actually don't even have to put the 5 in there because the y equation is going to take care of itself. It's just always negative whatever x is. In this case, x is 5 minus 6t minus 4. It's x minus 4 squared plus 6. That's all there is to it. Those are the parametric equation of the child's motion. Now, her brother Stephen, who's now a senior chemical engineering major at a university here in America, is he's dancing as he moves along the horizontal line modeled by the x-axis. His velocity is a function of time in yards per minute is that. Find total distance. You got to watch out on the AP test. Sometimes they ask for total distance. Sometimes they ask for displacement. Look at the graph of this velocity function as a function of time. V is a function of time. What's going on with this? It's a sine function that has a period of what? Amplitude of 3, period of, hello, can someone spot the period for me based on the equation? What?
Pi.
Yeah, it's 2 pi over 2, which is pi. So that's his velocity. And so that's like pi over 2, pi over 4. We're at 5 pi over 4. So total distance traveled. Looks like he's moving to the right. And then for the first pi over 2 minutes, and then to the left. And then 5 pi over 4 is, pi is 4 pi over 4. So then you go another 5 pi over 4 is like 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. In terms of total distance traveled, he moved to the right, positive velocity, then he turned around and came back left. So at time 4 pi over 4, he's back where he started, isn't he? You see, is that your interpretation of the graph? He moves to the right, moves to the left, and so really, the total displacement is different than total distance. So displacement would be easy. That would just be the integral from 0 to 5 pi over 4 of v of t dt. It's kind of like net accumulation of a rate of change in the rate of snowfall. Instead of the rate of snowfall, I mean, come on, if you just want to know how much snow is on the ground, just it's like a total displacement problem. But if you want to know, total displacement, so it's like final minus initial, there it is. But they're asking total distance. So they want to take all of this distance plus all of that distance, treat them both as positive numbers. When they're talking total distance, then you need the integral from 0 to 5 pi over 4 of the absolute value of the velocity. So we have to take that as positive area. Basically, how many of these are there? Really, by symmetry, all you would have to do is integrate from 0 to pi over 4 and multiply it by how much? This is 3 sine of 2t dt. I mean, the total distance would be basically this treated as positive area, that treated as positive area, and this treated as positive area. So if I were to just take the integral from 0 to pi over 4, by what factor would I have to multiply that so that I get all of the total distance? Max?
5.
Yeah, it's 1, 2, it'd be 5 of those, 1, 2, 3, 4, 5. So I'd have to take 5 of those to get the answer to this problem. That's a way to deal with the absolute value. Okay, so that's just a review of some things. We need to move into the new material, which is the calculus of parametrics. In this course, in AP Calc BC, we do calculus of rectangular functions, calculus of parametric functions, calculus of polar functions, and calculus of vector-defined functions. Now, the good news is that vector-defined functions are just parametric functions reformatted. So if you learn the calculus of parametric functions, then you've got the calculus of vector functions, except for just a few notational changes. Conceptually, vectors are parametrics. So we're learning calculus of parametric functions today. We'll learn the calculus of polar functions the week after spring break. And then we won't have to spend as much time on vectors because everything that we learned in calculus of parametric functions applies to the calculus of vector-defined functions. So that's how we're going to finish up the course. Let's take a look at the big idea. Let's take a look at the parametric form of the first derivative. Keep in mind, first of all, that when you have a parametric function, you're going to have some sort of function of t for the x parametric equation, some other function of t, I'll call it g of t for the y parametric equation. And then there's a motion. It might be a baby crawling around, or it could be a baseball flying through the air, but one way or the other, you have a path. And this path, yeah, question.
We don't have this page.
But yeah, that page, the calculus of parametric functions appears to be not included in hand. Unfortunately, there's not much to draw on it, so you just have to put it on a, just pull out a sheet of paper. Does anyone need a sheet of paper? I'd be happy to provide it for you. If you need a sheet of paper, look, right here, come grab a sheet. So, all you gotta do is draw a curve with a tangent line on it. And let's say that generically, x and y are the parametric equations of this motion. So set up an axis with an x-axis, a y-axis, and we're going from A to B on the x-axis. Now, I would like you to write dy dx as the magnitude of what amounts to a velocity vector. We can break it up into the horizontal component dy dt, and the vertical component, the horizontal component is dx dt, which is the derivative of the x parametric equation. And so, again, this is a velocity vector, but it's also the slope of the tangent line drawn to the curve. So we're going to break this up into a horizontal vector of dx dt and a vertical component dy dt. Now, this is like baby Elia. She's moving at, let's say, 3 feet per second to the right. Let's say she's moving 4 feet per second vertically. So that means that she'd be traveling dy dx, I mean, this is the rate of change. She's traveling 5 feet per second. If you had a baby traveling 3 feet per second to the right and 4 feet per second up, it's a 3, 4, 5 triangle, then the resultant velocity vector would be 5 feet per second. So you can take a vector quantity like a velocity and resolve it into its horizontal component and its vertical component. So dy dx, the slope of the tangent line, is also the magnitude of the velocity vector for a baby traveling along this path. So, how do we find the slope of c, which would also be the magnitude of the velocity vector? The slope of c at x comma y. This is a curve. We're just calling the curve c. So the slope at x comma y can be thought of as rise over run, or dy dt over dx dt. And that is the formula for the derivative of a parametrically defined function. You could also call it y prime, because that's also dy dx. So there it is. It's just, we're back to rise over run, friends. Rate of change in the y direction divided by rate of change in the x direction. All you gotta do to find the derivative of a parametrically defined function is to take the derivative of the y parametric equation divided by the derivative of the x parametric equation. It's super straightforward. Nothing really mysterious here at all. It's like a big deal, so let's put a box around it. How about the second derivative? Second derivative is where people trip up. On the second derivative, though, you can avoid tripping up if you replace both of the y's with y primes. Because the second derivative of y with respect to x is the first derivative of y prime with respect to x. So y double prime, the second derivative of y with respect to x, is the first derivative of the first derivative. It's dy prime dx. Now we're at a point where we can just mechanistically use this formula. Every time you see a y, replace it with y prime, and you get dy prime dt over dx dt. And the thing that's confusing about this formula for y double prime is that there's a prime on the y, but there's no prime on the x. And that throws students off. However, it's exactly what the formula for first derivative of a parametrically defined function requires. Any questions on the parametric function for second derivative of a parametrically defined function? Let's turn the page and practice this stuff. So here we go. hopefully you have this page in your packet. So this teenager has parametric equations. X is 2t, y is 3t minus 1. We want to find the first derivative and the second derivative at the given value of the parameter. Here the parameter is t, so at t equals 3. So it's not too hard. Find y prime. Y prime is dy dt over dx dt. So dy dt, no big deal. Dy dt is just 3, dx dt is 2. So it's 3 halves. When you evaluate 3 halves at t equals 3, there is no t. You can think of it as 3 halves plus 0t. So the answer is 3 halves. So look how easy it is to get. I mean, if this were positioned as a function of time, all that means is that this person is traveling at 3 halves miles, or 3 over 2 miles per hour. So they're traveling 2 feet per second in the x direction, 3 in the y direction. And so when you take dy dt over dx dt, you get 1.5 would be an understanding of the velocity. Let's take a look at the second derivative. So on the second derivative, we have to take dy prime dt over dx dt. Well, we've already found y prime. Y prime is 3 halves and its derivative is 0. Dx dt we've already found is 2, so the answer is 0. So 0 evaluated at time 3 is 0. It's a constant function. It doesn't matter what the time is. So that's kind of an example that's so trivial that it can be confusing. So instead, to look at something more interesting, let's take a look at this parametric function, which, by the way, if you look at it in terms of the real world, hopefully you see that this is an ellipse. It's not a hyperbola. If you were to eliminate the parameter, which I'd like us to do kind of up in the margin, based on what we learned yesterday, we should be able to eliminate the parameter here by writing sine squared theta plus cosine squared theta equals 1. And when you replace sine theta with x over 2, this will be x squared over 4. And when you replace cosine theta with y over 4, you have plus y squared over 16 equals 1. So it's really an ellipse. It's an ellipse centered at the origin with x-intercepts at plus or minus 2, y-intercepts at plus or minus 4. Let's draw the ellipse. And by the way, if you're to look at the x versus t and y versus t, x versus t is 2 sine theta, y versus t is 4 cosine theta, so it starts at the point 0, 4. So we're starting up here at theta equals, when theta equals 0, it's not t equals, but theta equals 0. We're up there at the top. And then at pi over 2, x has maxed out at, this is x versus t sine curve, so it's maxed out at 2, and y is at 0, so it's 2, 0. So here we are at theta equals pi over 4, we must be moving that way. And what they want to know is that 5 pi over 6 is going 1 pi over 4, 2 pi over 4, 3 pi over 4. It's like, what's going on? We can find the location of the person who's moving around in this elliptical motion at theta equals 5 pi over 6 by just plugging 5 pi over 6 in for theta. So where are we located at 5 pi over 6? At theta equals 5 pi over 6. Let's just substitute 5 pi over 6 in for theta. Using my pre-calculus, I know that the sine of 5 pi over 6 is 1/2, and half of 2 is 2. So we're at the point 1, comma, and so I'll look at one thing real quick. Yeah, we're good. Pi, oh, I see what happened there. And that's at pi over 2. I kept saying pi over 4, but at pi over 2, we're at the point 2, 0. So that means at 5 pi over 6, we're likely to be, since this is pi down at the bottom, theta equals pi. So 5 pi over 6 is, the person has made it from here down to there. And so really what the question is asking for, to find dy dx is to find the slope of this red tangent line drawn to the ellipse at the point, well, and that's what we're trying to figure out. X is 1. The y coordinate to that point of tangency is found by putting 5 pi over 6 in for theta here. So cosine of 5 pi over 6 is negative radical 3 over 2 times 4 is negative 2 radical 3. So negative 2 radical 3. And it makes sense from our graph of the ellipse. It looks like the coordinates of this point could plausibly be 1 comma negative 2 radical 3. This question is asking us to find the slope of the tangent line drawn to the curve at the point 1 comma negative radical 2 over 3. So let's proceed. Let's use our formula using the calculus of parametric equations. Let's find dy d theta over dx d theta. Would you go ahead and perform those calculations? Take the derivative of the y parametric equation divided by the derivative of the x parametric equation to find the slope of the tangent line at that point. Okay, I took derivatives, simplifying to get negative 2 tangent theta. And they want us to basically evaluate that at 5 pi over 6. So if you evaluate that expression at theta equals 5 pi over 6, it seems to me like the tangent of 5 pi over 6 is negative radical 3 over 3. So we're going to take negative 2 times negative radical 3 over 3 to get 2 radical 3 over 3. Positive number. That's consistent with what we see in the graph. We see a tangent line with positive slope. The slope of that tangent line is 2 radical 3 over 3. And let's kill 2 birds with 1 stone here, because later in the lesson we have to find equations of tangent lines using this. So you would just use y minus y1 equals m times x minus x1. The equation of that red tangent line is y plus 2 radical 3 equals the slope, which is 2 radical 3 over 3 times x minus 1. So we can skip that problem later on when we get to it. I mean, we're just using the slope of the tangent line to find the equation of the tangent line, the kind of stuff that we did back in Unit 2 of this course. So now we have to find the second derivative. To find the second derivative, we've got to be a little more careful. First, we have to take dy prime d theta over dx d theta. Now, the good news here is we've already calculated dx d theta. It's 2 cosine theta, so let's recycle that from the previous problem. Dy prime d theta, we have dy prime sitting right there. So we're going to take the y prime, that was the answer to the first part of this problem, and we're going to take the derivative of it again to get dy prime. Derivative of negative 2 tangent theta is derivative tangent secant squared, so it's negative 2 secant squared theta. 2's cancel, you get negative 1 over cosine cubed theta when you do the basic trigonometry. Move the secant squared to the denominator is cosine squared. So, it's negative secant cubed, but when it comes to evaluating this expression at theta equals 5 pi over 6, I go ahead and do the trigonometry, evaluate negative 1 over cosine cubed theta at theta equals 5 pi over 6. And if you do it right, by the way, should get 4 radical 3 over 3. It's just a matter of substitution, reviewing your free calc. The significance of this is that the ellipse should be concave up, because the second derivative is positive. The graph of the ellipse should be concave up. And look, it is. The ellipse is concave up at the point 1 comma negative 2 radical 3. Any questions on this example? Given the parametric equations, find the first and second derivative and interpret it in the context of the graph. Okay, for the sake of time, we're going to skip this problem and we're going to focus on number 2 right here. So would you please, based on our review of yesterday, go ahead and eliminate the parameter. Let's see what this thing looks like using tan in one section. Go ahead and eliminate the parameter, even though that's not what they're asking for. We just want to get a quick graph of this hyperbola so that we can see if our calculus is appropriately harmonizing with the pre-calculus. Okay, it looks like the hyperbola I'm getting is x squared over 4 times y minus 1 squared over 4 equals 1. That's an x hyperbola that's been shifted.
It's x minus.
Why is his next one?
So secant x over, oh yeah, no, it's not
X
x.
minus 2 over 1.
Yeah, it's x minus 2 squared over 1. Thank you. So x minus 2. Okay, so this is going to be x minus 2. So that means that the center of the dotted box will be at the point 2 comma 1. Just to get a picture of this, let's sketch a graph in which the center of the dotted box at the point 2 comma 1 has, and yeah, that's over, we said it was over 1, right? Okay, so that means from the center of the dotted box, we go plus or minus 1 in the x direction, and we go plus or minus 2 in the y direction. So the bottom of the dotted box is at -1, top is at 3. So here's the dotted box of my hyperbola. It is an x hyperbola. I'm going to draw the diagonals and extend them. So we're performing calculus on this hyperbola, which I have here in red. It has a branch that opens to the right and another branch that opens to the left. And we're being asked at theta equals pi over 3, well, where are we at theta equals 0? Let's do quick sketches of the parametric equations. X is a function of theta. So we can get oriented to what's happening here. This is shifting up 2, and then the guide graph would be like that. So we've got a secant function that starts at 3 and goes up and comes up there. So the y versus t graph is a tangent function that's been shifted up 1, and it has a vertical stretch factor of 2, but for our purposes, all we do is sketch the basic tangent graph. The point is we're starting at the point, x is 3, y is 1. I see where that is. 3 comma 1 is right here. So here we are at theta equals 0. And according to my tangent graph, pi over 3 is not quite pi over 2. So this is, x is going to increase and y is increasing. So by the time we get to theta equals pi over 3, we're going to be up here somewhere. So when they're asking us for dy dx, it's really the slope of the tangent line drawn to the hyperbola right here. So we better get a positive answer for the slope, because I can tell by the graph generated using my pre-calculus skills that the first derivative is positive. By the way, notice the graph, is that concave up or concave down right here? Can you read the concavity from the graph?
Concave down.
That's concave down. So the first derivative better be positive, the second derivative better be negative. Go ahead and evaluate the first derivative at theta equals pi over 3. Go ahead and do the calculus on that, see what you get. Okay. So if you did y prime correctly, dy d theta over dx d theta. So 2 secant theta over tangent theta becomes 2, so it came out to 2 secant theta over tangent theta when you simplify it, and that becomes 4 radical 3 over 3. So that's the slope. The second derivative is going to be, well, let's see, 1 over cosine, sine over cosine. You can actually simplify that further, because 2 secant is 2 over cosine, tangent is sine over cosine, so the cosines cancel right there, it's just 2 over sine. So the y prime is 2 cosecant theta, so y double prime would be the derivative of 2 cosecant theta, which is negative 2 cosecant theta cotangent theta over a recycled dx d theta. So that's going to be secant theta tangent theta. Okay, so the point is you have to simplify that and evaluate it. You'll get a negative answer, but for the sake of time, we're not going to complete that. We need to make sure we get all the new concepts. So, in terms of making sure we get the new concepts, I want to make sure that you get the arc length formula. So flip forward to the arc length formula. There are 3 of them in this course. You've already studied one of them. Rectangular arc length, S, the length of the arc, would be the integral from A to B of the square root of 1 plus f prime of x, derivative squared dx. That's review. You've seen that before. It's based on the Pythagorean theorem. Now, parametric arc length S, the length of the curve, sometimes we use S for arc length, is also based on the Pythagorean theorem. It's based on, so at time 1, we're located here at x1, y1. At time 2, we're located on the curve at x2, y2. What is basically you can use this for calculating total distance traveled. How much distance did you travel from time 1 to time 2? This comes out to the integral from t1 to t2 of the square root of, and once again, just like over here we squared a derivative, it's going to be the derivative of the x parametric equation, dx dt quantity squared, plus the derivative of the y parametric equation, dy dt squared dt. While we're here, I'm going to give you polar arc length, even though we haven't reviewed polar functions yet. Polar arc length, so that you have all 3 formulas here in the same spot, is the integral from alpha to beta of the square root of r of theta, quantity squared, plus the derivative r prime of theta, quantity squared, and outside the square root is a d theta. You just want to make sure you had all of the arc length formulas for the course combined. Now, back it up. Previous page, the page that we skipped. This is one in which we see, here we found an equation of the tangent line. Do you remember I multitasked on that previous problem? So we've done equation of the tangent line. Now, points of horizontal and vertical tangency. Let's do just this problem with the time that remains. There is a pre-calculus approach to finding the points of horizontal and vertical tangency and a calculus approach. Let's compare the pre-calculus and the calculus approach. In the pre-calculus approach, just sketch the graph after you eliminate the parameter. So let's call this pre-calculus. In pre-calculus, we would eliminate the parameters sine squared theta plus cosine squared theta equals 1. Eliminating the parameters can be x minus 4 over 2 squared, so it's x minus 4 over 2 squared, similar to what we did earlier. For cosine, whoops, I think I got that mixed up. I'm gonna erase that because that's sine. Yep, I got the other one in there. So when you solve for sine, you get just y plus 1. So it's y plus 1 quantity squared. When I solve the first one for cosine, I get x minus 4 over 2 quantity squared equals 1. This is an ellipse. So to clean it up a little bit, it's just x minus 4 squared over 4 plus y plus 1 squared over 1 equals 1. This is an ellipse centered at the point 4 comma negative 1. So in my pre-calculus approach, I just sketch the graph. 1, 2, 3, 4, comma negative 1, that's the center of the ellipse. And then I go plus or minus 2 in the x direction. So plus or minus 2, that's from 2 to 6. I go plus or minus 1 in the y direction. So my ellipse is right here, and I can find the points of horizontal tangency by simply inspecting the graph. Where are the horizontal tangents? Here they are in red. That's a horizontal tangent. There's 2 of them. The points of horizontal tangency are 4, 0 and 4, negative 2. Pre-calculus in this case worked pretty quickly. However, let's compare that to a calculus-based approach. In the calculus-based approach, let's separate that out. We're not doing this problem. So now let's take a calculus-based approach to this problem, which, by the way, you're not always going to be able to sketch the graph. That's why we need a calculus-based approach. Pre-calculus has very limited, because it's rare that you're able to actually get the graph by hand. In the calculus-based approach, if you want to find the points of HT, horizontal tangency, here's how we roll. We know that dy dx, the slope of the tangent line is, using today's formula, dy d theta over dx d theta. Now, sometimes they ask you to find points of vertical tangency. Let me tell you right now, horizontal tangents occur when dy d theta is 0. Guess when the vertical tangents occurred? When dx d theta is 0. So what I'm going to lead you through here to find horizontal tangents, basically you have to find the values of theta at which the horizontal tangents occur, is basically the same approach that you would use to find the point at which vertical tangents. I mean, we know the vertical tangents occur over here at 6, -1 and 2, -1. You could get that from calculus by setting dx d theta equals 0. So you might want to say set equal to 0 for points of VT, vertical tangency. In class here, let's just set dy d theta equals 0 to get the points 4, 0 and 4, -2. So dy d theta equals 0 is the beginning step of my work. And dy d theta is derivative of that, that's going to be cosine theta equals 0. So to find the theta values at which this occurs, draw a Mach diagram, cosine theta equals 0, that's at theta equals pi/2, and theta equals 3 pi/2. Those are the two values of theta at which cosine theta is equal to 0. So, to find the x and y coordinates of the points of horizontal tangency, first I put pi/2 in for theta. So, let's take x, y, evaluated at theta equals pi/2, according to the parametric equations. When theta is pi/2, cosine pi/2 is 0. So we get 4, and now put pi/2 in for theta here, sine of pi/2 is 1, -1 plus 1 is 0. So we still get the point 4, 0 like we did in the pre-calculus approach. Now, according to the Mach diagram, we have to let theta equal 3 pi/2. Well, come on, it's the same thing. It's going to be 4, -2. When you evaluate the first derivative, or when you evaluate the parametric equations at theta equals 3 pi/2. So you'll get 4, 0 and 4, -2 using the calculus approach. It harmonizes with the pre-calculus approach. So we have 45 more seconds. I want you to hit the last page of the handout, which should look like this. And this is just a review of something that we've done many times in the course. And since it is review, we're going to put it in here. Cars moving, it starts at time 5. At time 5, it's located here. If you want to find its x coordinate at time 20 and its y coordinate at time 20, guess what? X final equals x initial plus the change in x. And y final equals y initial plus the change in y. We've been doing these all year. But here's the derivatives of the parametric equations of the motion, which is actually sweet because it's easy to find. You just take this, we start at the point 5, 5, and then we take, we're starting at point 5, 70. So we're at the point 5, 70. We integrate from 5 to 20 of dx dt, and here we integrate from 5 to 20 on dy dt, because just like in the snowfall problem from New York City, a definite integral is a net accumulation of a rate of change. So this is just a calculator problem where you use Math 9, FNINT, to take the given dx dt, integrate it from 5 to 20, take the given dy dt, integrate it from 5 to 20. That concludes the lesson. Have a great spring break.